Good evening.
Good evening, sir.
Good evening, sir. Namaskar.
So we'll wait for 5 minutes. Let others come. We are two only here.
Sure, sir.
Okay, we'll start. I think others will not come. They will not join. Anyway. So, in our last class yesterday, we have discussed the ultraviolet visible spectroscopy or UV visible spectroscopy. The second chapter of your syllabus, it is no chapters are there. Okay. Anyway, the next part is the IR spectra, basic aspects and applications, instrumentation, sample handling, characteristic vibrational frequencies of alkanes, alkenes, alkynes, and aromatic compounds, IR spectra of alcohol, phenol, ether, and amine. And moreover, then we'll move to some more classes of organic compounds like carbonyl compounds, aldehyde, ketone, carboxylic acids, derivative of carboxylic acid, esters, amides, anhydrides, lactones, lactams, all these things are there. Then effect of hydrogen bonding and solvent effect on vibrational frequency overtones, combination bands, and Fermi resonance. So let's hope Let's see how much we are covering. So, as already we know, the infrared spectrum, it is an important record which gives the sufficient information about the structure of a compound. Structure of a compound means here, as we have discussed, am I audible?
Yes, sir.
A screen is visible or not?
Sir. Visible, sir.
Okay, okay. Thank you. So, UV and visible radiation that is having higher energy than infrared radiation. Infrared radiation is having longer wavelength than UV and visible electromagnetic radiation. So, due to lesser energy, when any molecule is irradiated with infrared or visible light, then there will be electronic transition. So that's why UV visible spectroscopy is also known as electronic spectroscopy. But here in infrared, when infrared radiation is observed by a molecule, there will be a change in the vibrational energy level, not the electronic energy level. So from electron will shift from one vibrational level to another vibrational level in the same electronic level, because vibrational energy is less than translational energy. So therefore it is also known as vibrational spectra. And as you know, each vibrational level is also associated with some rotational energy level. So that's why it is known as vibrational rotational spectroscopy. And the range is given here. The generally the infrared region is 2.5 micron to 15 micron, and below 2.5, that is 0.8 micron to 2.5 micron, is called near infrared, and 2.5 to 15 is infrared, and 15 micron to 200 micron is called far infrared region. So this is the spectrum: near IR, IR, and far IR. So in infrared, when we are going for taking the spectrograph, we are representing in x-axis we are taking the observance, but in y-axis we have to take the wave number, not the wavelength. So wave number, as you know, wave number is the reciprocal of wavelength. So wave number you have to take in wavelength, you have to measure in centimeter. So wave number will express in centimeter inverse. So you can see here, if the wavelength is 2.5 micron, as in case of infrared region, so corresponding wave number is 4000 centimeter inverse, and 2.5 micron to 15 micron. So 15 micron, if wavelength will be 15 micron, then corresponding wave number will be 667 centimeter inverse. So we have to represent the spectra in x-axis. We have to represent the wave number in centimeter inverse. So this is the calculation that you know. And observance, already we know, that is the reciprocal of transmittance. So logarithm of 1 by t is known as observance. So now, what is the principle of infrared spectroscopy? The observation of infrared radiation causes an excitation of molecule from a lower to higher vibrational level. So when it will move from one vibrational level to another vibrational level, and each vibrational level is associated with rotational level also. So infrared spectroscopy is also known as vibrational rotational spectra. So all the bonds in a molecule are not capable of absorbing infrared energy. Just you remember this one. Here the vibration takes place. That means the bond, the electron, they will vibrate. That means the bond between two atoms in a molecule, there will be vibration. That means each constituent atoms, they will vibrate with respect to one another. Okay, would you follow what I am telling? Electron will vibrate means the bond or the atom will vibrate, because electron, the bond pair of electrons, if there will be vibration, then constituent atoms which are joined together by a particular bond. So there will be vibration. So here it is written here, all the bonds in a molecule are not capable of absorbing infrared energy, but only those bonds which are accompanied by a change in dipole moment will absorb in infrared region. So if the bond will be polar, then only it will absorb in the infrared region, and there will be vibrational transition. So in that way, the vibrational transitions of carbon C double bond O, NH, OH, these bands are accompanied by a change in dipole moment. Thus, they will absorb strongly in infrared region. But transition in carbon-carbon bond in symmetrical alkenes and alkynes are not accompanied by a change in dipole moment, and hence they do not absorb in infrared region. So the theory of molecular vibration. So these vibrational and rotational bands which will be formed. So the absorption of infrared region in the infrared region is due to change in the vibrational and rotational level. So when radiation with frequency range less than 100 centimeter inverse are observed, molecular rotation takes place in the substance, because you can see infrared region is from 4000 centimeter inverse to 667 centimeter inverse, but when less than 100 centimeter inverse, so we can write it as frequency also, because 1 by lambda c equal to nu lambda. So frequency 1 by lambda is related to frequency. It is known as wave number, but we can say as frequency also. So the frequency range less than 100 centimeter inverse are observed. So rotation takes place because it is still lesser than infrared region. It will be in microwave region. So rotation takes place. So as this absorption is quantized, discrete lines are formed in the spectrum due to molecular rotation. So molecular vibrations are also set in when more energetic radiation in the region 10 to the power 4 to 10 to the power 2 centimeter inverse are passed. So that's why the vibrational rotational bands will occur, will get the band only. So this vibrational energy, it depends upon the mass of the atom present in a molecule, strength of the bond, and arrangement of atoms with the molecule like cis strands or enantiomers. So it has been found that no two compounds except the enantiomers can have similar infrared spectra. So different compounds will have different infrared spectra. No two compounds will have the same spectra except the enantiomers. Enantiomers mean the optically active compounds D and L isomer are known as enantiomer. So now when the molecule observed in the infrared region, there will be vibration. So the vibration may be of the two types of fundamental vibrations are there. One is stretching, another is bending. So stretching vibration, in this vibration the distance between two atoms increases or decreases, but the atom remains in the same bond axis. You can see this one. This vibration is stretching vibration. In the spring and ball model, it is explained here, because we can stretch the string, and string is related the spring is related to the bond, and the ball is the atom. So when the two atoms, they will move away from each other or come closer to each other, but on the same bond axis, then it is known as stretching vibration. But this one is the bending vibration. So they will come closer, they will go, or they will go away from each other, or one will come up the plane, one will be below the plane. Different types of bending vibrations are there, we'll discuss. So in stretching vibration, on the same bond axis, the two atoms, they will vibrate, means they will come closer or they will move away from each other. So that is stretching. So in bending vibration, the position of the atoms changes with respect to the original bond axis. This is the bond axis, but position of atom changes. It may vibrate, like it will bend like this will bend like this. So this is one type of stretching. It these two will come closer to each other or move away from each other with respect to this atom. And different types of vibrations are there, or both will move this side or that side. Okay, and both will move up and down, and one will move up, one will move down. So four types of bending vibrations are there. We'll discuss this one. So types of stretching vibration. There are two types of stretching vibration: symmetrical stretching and asymmetrical stretching. In symmetrical stretching, at a time, both the atoms they will move away or they will come closer. But asymmetrical stretching, one will move away, one will come closer. In this, see, it's written here in this type, the movement of the atoms with respect to a particular atom in a molecule is in the same direction. Here, one atom approaches the central atom while the other departs from it. That is asymmetric stretching. Then types of bending vibration or deformation. Bending vibrations are four types, as I told: scissoring, rocking, wagging, and twisting. So scissoring, when both will come closer to each other. So this type of vibration is scissoring. Then rocking. So both will move in one direction. This in this direction, this is this direction or this direction. So like this, it is rocking vibration. And here wagging, both will move up and down the plane simultaneously. Wagging means, I think you have seen, you know what is wagging. Can anybody tell what is wagging? All are Odia or any?
Yes, sir.
All of you understand Odia or not?
Little.
Okay. Any other thing, Pramodini or anybody? What is wagging?
Pardon, sir?
What is wagging? Wagging. What do you mean by wagging? This vibration. उसमें क्या करते हैं? चावल
I
लेके
think
ऐसे ऐसे
I
करते हैं ना. हाँ,
so
बोलिए.
to and fro
To
movement
and
are you talking about?
to and fro means one. Both will move up and down.
Okay.
Side to side or to sec up and down?
Both will up the plane and down the plane. Over, up and down. In ODI, we are
Okay.
telling that kula, kula.
Okay, understood, sir. Understood. Cool.
Kula, you understood?
Yes, sir.
चावल लेके ऐसे करते हैं ना.
Yes, sir. Yes, sir. A few days back
Okay.
here, they were selling due to this, what is called Durga Puja or something.
Okay. So that is wagging.
Okay.
Anyway,
Yes, sir.
so both will move up and down. Here, one will move up, one will move down. That is twisting. This is, you can imagine that one. Twisting motion. One will move up, one will move down. So both in the same direction means this is rocking, and one will move up, one will move down. This same direction means they will, can you imagine this one. Yeah, here also. If they will move both as shown by arrow, this motion is scissoring. But when both will be in this direction or in this direction, then it is rocking. Both will move up the plane and down the plane, that is wagging. One will move up, one will move down, that is twisting. So four types of bending vibration and two types of stretching vibration. So it depends upon the bond length and bond strength, what type of vibration they will observe, and it depends upon the strength of energy, amount of energy which will be observed during the infrared spectroscopy. Now, if you move to the theory part, what will be the fundamental vibrational frequency? That means in centimeter inverse, how to find out that one? It is represented by nu bar, which is 1 by lambda, or it is nu by c. As you know, c equal to nu lambda. So 1 by lambda equal to nu by c, or it is nu bar, the wave number. So can be found out from Hooke's law. In Hooke's law, as you know, the frequency of vibration, nu equal to 1 by 2 pi k divided by mu. Mu is the reduced mass, which is M1 M2 by M1 plus M2. If M1 is the mass of one atom, M2 is the other atom, which are covalently bonded with each other, then reduced mass of the molecule will be by the formula M1 M2, M1 into M2 divided by M1 plus M2, which is equal to mu. So mu is the reduced mass. So Hooke's law tells that the vibrational frequency nu equal to 1 by 2 pi k by mu to the power half or root over of k by mu. But we want to find out the wave number. Okay, that is nu bar, which is reciprocal of 1 by lambda. So 1 by lambda will be equal to nu by c. So we have to divide this one by c. So fundamental frequency or the wave number nu bar will be equal to 1 by 2 pi c into root over of k by mu, where mu is the reduced mass and k is the force constant. And generally, for a single bond, the value of k is approximately 5 into 10 to the power 5 gram per second inverse. Gram per second square or gram into second inverse. And c is the velocity of radiation. As you know, velocity of light 2.998 into 10 to the power 10 centimeter per second. And this value of vibrational frequency, now you can see vibrational frequency means nu bar. It depends upon what? Velocity of light is constant, so it depends upon the force constant. That means bond strength and reduced mass. So depending upon the force constant or bond strength and reduced mass, the vibrational frequency or the wave number will vary. Now, we can see the example. One example we'll give. Let us calculate the approximate frequency of carbon-hydrogen stressing vibration from the following data. Value of k is given 5 into 10 to the power 5 gram per second square, and mass of carbon, as you know, it is how much in atomic mass unit? It is 12 AMU. If you convert it to gram, it is 20 into 10 to the power minus 24 gram. And mass of hydrogen is 1.6 into 10 to the power minus 24 gram. Are you clear about this one? Mass of carbon and hydrogen.
Yes, sir.
How it will be 20 into mass of carbon is 20 into 10 to the power minus 24 gram. And what is when you are telling the atomic mass of carbon, you are writing 12 gram or 12 AMU. What is the relationship between gram and AMU? Atomic mass unit.
So it is atomic mass unit, and when we are expressing in gram, that is we are expressing the mole total, that is Avogadro number 6.023 into 10 to the 23.
Thank you. AMU when multiplied with Avogadro's number, we will get the mass in gram. Okay, so this is mass of one carbon atom. So mass of 1 mole of carbon atom is 12 gram. So obviously mass of one carbon atom will be 20 into 10 to the power minus 24 gram. And that of hydrogen, this one. So from here you calculate the reduced mass. Force constant is given 1 by 2 pi. You will get the frequency. So frequency is 9.3 into 10 to the power minus 10 to the 13 second inverse. And when you find out the wave number, so that will be equal to nu by c. You have to divide it by c, or directly you can divide here. You can find out the wave number, which is equal to 1 by 2 pi c root over of k by m1 m2 divided by m1 plus m2. So obviously it will come 3100 centimeter inverse. These are the fundamental frequencies. Some of values you have to remember. Okay, this is the stressing vibration of carbon hydrogen bond, where, for example, you have methyl alcohol CH3OH. So then what type of stretching vibration you will observe there? You have a methyl group which contains carbon hydrogen single bond, and you have one hydroxyl group OH, or carbon oxygen bond and oxygen hydrogen bond. Yes or no? So three types of bonds live there. 3 number of carbon hydrogen bond, one carbon oxygen bond, another oxygen hydrogen bond. So in all the bonds there will be stretching and bending vibration. So when we are measuring you see here we have measured the stretching vibration of carbon hydrogen. So in case of methyl alcohol for methyl group or for methylene group CH2, if CH2 group is there, so the CH stretching vibration will be observed at 3100 centimeter inverse in the infrared spectroscopy. So similarly, for C double bond C, if it is a double bond, you see we have given the force constant, value of force constant is 5 into 10 to the 5 for a single bond. But when there will be a double bond, carbon-carbon double bond, obviously the force constant will be nearly 2 times. So here it is written here, carbon-carbon double bond. For in this example, force constant is given K equal to 10 into 10 to the power 5 times per centimeter, and this one gram per second square. Both are same. Unit is same. Gram per second square or dyne per centimeter is having same unit of force constant. Convert it, you will get the same one. Okay. So anyway, so if you have the mass and using that formula, you can find out the frequency, vibrational frequency. Here you can see a carbon-carbon double bond. You go on calculating, you will get the vibrational stretching frequency at where? 1680. So around 1600 centimeter inverse, you will get a peak for carbon-carbon double bond. For carbon-hydrogen single bond, you will get a peak at 3100 centimeter inverse that we have discussed here. So similarly, you can find out by using this formula. Okay. So here are some problems, you can go through it. Now, the number of fundamental vibrations means how many, if any compound, as I told in case of methyl alcohol, 3 carbon hydrogen bonds are there, 1 carbon oxygen bond is there, and 1 oxygen hydrogen bond is there. So, how many fundamental vibration will get? So, that will be can be given by the formula energy of vibration, that will be equal to V plus half into h nu. So nu is the vibrational frequency, h is the Planck's constant, V is the number of vibrational levels and which can have the value 0, 1, 2 because it is quantized. So it will be 0, 1, 2 like this. So if you put here 0, then it will be half h nu. If it is 1, 3 by 2 h nu. So anyway, the difference will be h nu only. So that means it is quantized. Okay. So difference you can see it is S nu, so it is quantized, and number of fundamental vibrations as the heading. So it can be find out using some different formula and which is related to the degrees of freedom. So what do you mean by degrees of freedom? Sit in here. Okay. The number of degrees of freedom is equal to the sum of the coordinates necessary to locate all the atoms of a molecule in space. Okay. For example, you consider simply one atom. So one atom, if it is a single isolated atom, it will have linear motion or translatory motion which will have 3 degrees of freedom, either it may be in x-axis or y-axis or z-axis. So the translational motion will be expressed by 3 degrees of freedom, and moreover it will have a vibrational degrees of freedom if it will vibrate through its mean position, and it will have one rotational degrees of freedom. Single atom I am telling, but infrared spectroscopy deals with the molecule, not with the atom. So a molecule, simply consider a diatomic molecule. For example, carbon monoxide, CO. Am I clear? Are you listening to me or you are just signing,
No, sir.
Yes,
sign
sir,
in
we are
and
here.
okay,
Sir, here, listen.
okay, okay. Because let me see how many. One, two, three, four, five only. Okay. So our infrared spectroscopy deals with the molecule, not the atom. So for simplicity, let us take a diatomic molecule. Any diatomic molecule can take, let it HF, HCl, carbon monoxide, anything. So just imagine when it is how many types of what is the total number of or degrees of freedom means how many types of motion will be there. You know it will have translational, rotational, and vibrational. So the translational motion can be expressed by x, y, and z axis. So 3 degrees of freedom due to translational motion. Yes or no? Yes or no? If it will have translational motion that can be represented by 3 degrees of freedom means three coordinates, whether the motion is along x axis or along y axis or along z axis. So that is the degrees of freedom. So due to its translational motion, it will have 3 degrees of freedom. Then what about the rotational? How many rotational degrees of freedom will be there?
Sir,
When just
pardon, may I ask something? Sir,
yes,
hello? Sir,
yes, tell.
here as we are learning these things,
Uh,
so how to understand from the spectrum like this way that can we read like this or theoretically we have to remember these values, sir? Means
which one?
uh, this spectroscopy we are learning this one
Uh,
like one unknown molecule I'm injecting. I wanted to know
hmm.
what is the mass number and I want to identify that what is exactly over there. So if I do all these tests, then after that means what are the factors or parameter I should study that I can determine these factors like degrees of freedom and all this, or it is only related to theory in that way, not related to the practical.
Theory is related to practical. You should know the theory.
No. Actually, what I mean to say, sir, means when we get that spectrum, what are the parameters I should focus for so that I can get these values and I can correlate as theoretically it is said.
Okay, thing is that okay, we'll go to the spectra of a molecule,
Okay.
then we'll discuss.
Okay, sir. Thank you.
Okay, but before that, you
Okay.
just remember this one. What will be
Mm-hmm.
there? This is degrees of freedom is theoretical, but what I told here the vibrational frequency, two three, vibrational frequency I told 1600 and one is 3100. So these things it will be reflected in the spectrogram. Just I'll give the example. You can say this one. Okay.
Okay, sir.
But why I am discussing about the number of fundamental vibration that indicates how the peak looks like, whether it is sharp peak or whether it is a broad peak. Okay, anyway,
Okay.
let me show you a plot. Then you can yes, let this IR plot.
Yes, sir. This kind of means how to understand this.
Yes,
This one.
okay. Anyway, so here you can see what are the peaks here. One peak you are getting around 3001
2,900.
3100.
3,100.
This one,
Oh,
this
three.
peak, okay, this peak
Yes,
is
sir.
around 2900
Hmm.
nearly. I'm just roughly I'm telling,
Yeah, understood, sir.
okay, and these peaks, this is immaterial, this are noise only, and our fingerprint region is from this 1800 below 1800. Okay, from 2500 to 1800, this region is not, I mean, we cannot consider this one. Nothing will be there. This is
The
only
fingerprint
the,
region means you mean to say which will give us the exactly
the
means
functional
totally
groups.
identical what is it that identity
Uh,
will be revealed of that molecule that you mean to say
yeah,
fingerprint.
but in
Okay.
IR, infrared spectroscopy, will know only the functional groups, not the
Okay.
molecule as a whole. Okay.
Okay. Okay.
So here one peak I am getting around 1600. 1600 means it is the carbon-carbon double bond.
Okay.
Just now we have discussed if carbon-carbon double
Hmm.
bond, the vibrational frequency will come around 1600. So like that, these peak positions we have to just some positions we have to remember. Otherwise, we have to. There are some data are also there. Okay,
Okay.
in
So that
chemical
fingerprint
also
region you said that 1800 to
below 1800.
below 1800.
1700
Okay, sir.
something to 800. Let from 1800 to 800.
Okay.
This region is the fingerprint region. Above 18, we are not getting anything. Only this around 2901 peak, which is due to CH2, methylene group or methyl group, CH stretching, and if OH or NH will be there, alcohol in case of
Okay.
alcohol, in case of water. Okay, that OH stretching will get around 3400 to 3500. Here, we'll get a broad peak. Here it is not
Sir,
showing.
this fingerprint region is common for all, or it is like certain functional group based, like if this
It will
kind
be,
of
it will
compound?
be, it will be different. It will be
Okay.
different. The peak position will change, na?
No, sir, that fingerprint region, that region
Huh?
is same for all. But in that region, different functional group
Different,
peak
yes,
will
it
come
will
at
give
different
different
peak.
peak. Yes, yes.
Okay. Okay.
This, you see, in every spectrum, you can see this is known as the fingerprint region. Same thing here. See,
Okay.
this one. And whatever you are
Yes, sir.
getting here, that is for OH group and CH2, nothing else. But other functional group, all the functional groups, almost all, they will give the peak here. That you have to remember the position. See, carbon tetrachloride or carbon disulfide. Others are also there. We'll discuss one by one. It will come. You see, the fingerprint region is written here. The region below 1500 centimeter inverse each in many observations. I told 17. Here it is in 1500 because
So, sir, due
1735.
to metal chelating, these functional group stretching will get affected, or it does not have any such relation.
Metal chelating in case of.
In case of if copper is there, and
Hmm.
if I'm using this, so if it is getting chelated with some
Pardon, I could not hear. Hello.
metals, if getting chelated with like any lipids or any protein molecules, like in
Definitely, if there will be bonding, new bonding or chelation with organic compound will be there. Definitely, the that
so
absorption band
that
will change. Peak position will change.
yes, that is what. Okay, okay, sir.
Okay, it will change. Obviously, it will change. Okay, we'll see. Okay, we'll move to that one where we are there. Ah, sorry. Yes. Okay, so how to find out this one? The number of fundamental vibration. We can find out the translational frequency. We can find out the rotational frequency. So there is a rule to find out the vibrational frequency because total number of degrees of freedom is 3n. That you remember. Where n is the number of atoms in a molecule. Okay. How? If there is only one atom, then total number of degrees of freedom will be only 3.
Yes,
That
sir.
is the three translational degrees of freedom. Vibrational, when you're telling vibrational motion means with respect to another, how it will vibrate. Understood?
Yes, sir.
Because vibrational, when I give this figure with respect to one atom, the other is vibrating. Or is that stretching, bending, all in so yes, here. With
So
respect to
all these
this
are relative. That is, they are.
relative, at least two will be there. With
Okay.
respect to this, how it is vibrating.
Okay.
Okay, now let you just remove this one diatomic molecule. Here we will discuss. Let these other figures are not there, so I am telling this one. So let these two atoms are there, a diatomic molecule. So this molecule will have translational motion in x, in y, and in z direction. So three
Yes.
translational degrees of freedom. And what will be the vibrational degrees of freedom? It may stretch, it may
Okay.
bend. Okay.
Yes, sir.
And stretching, if you are considering the stretching is one stretching only. And what is the rotational degrees of freedom? It may rotate if Z, let this axis is Z axis, which is the internuclear axis. So rotation can take place in X axis and Y axis, not in Z axis. Just hold your pen and just imagine. You can rotate it along x axis, along y axis, but not along z axis. When you are rotating along z axis, because z axis is the internuclear axis, that the axis which is the bond, which contains the bond. So rotation around the internuclear axis is impossible. Impossible means it is unmaterial. The position will not change.
So we meant to say that we can say that it is due to inertia.
Not
Means.
inertia. You just hold your pen on your
Hmm.
hand, rotate it
Okay.
in one direction and
Hmm.
another direction perpendicular. Can you
Hmm.
imagine?
Yes, sir.
And one is just hold the pen and rotate. Means just like in two finger, you just rotate. That is the z axis.
Okay.
So when you are rotating, see, if you let this is the internuclear axis. Notice if there will be a linear. Any line you consider otherwise? Where is the line? In the figure there is no line. Okay, let this line, whatever is there. If you rotate it in this direction, okay. So this is
Yes.
let x-axis you are rotating. So
Hmm.
this line will rotate,
Yes.
and if in a perpendicular direction means if you rotate then it will rotate. But if you rotate like the along here, if you give the circular motion, so the position will not change. Can you imagine x and y, if z is the internuclear axis, around z axis rotation is immaterial for a diatomic molecule. So therefore, it will have only two rotational degrees of freedom. So two rotational degrees of freedom, three translational degrees of freedom, total number of molecules. Total degrees of freedom will be how much? 3n.
Yes.
N is the number of atoms present in the molecule. Would you follow?
Yes, sir.
So then, yes, total degrees of freedom, that is equal to 3n, which is sum total of translational degrees of freedom, rotational degrees of freedom, and vibrational degrees of freedom. So, in case of a diatomic molecule, you have three translational degrees of freedom, two rotational degrees of freedom, not three. In around the internuclear axis, rotation is immaterial. Only perpendicular to internuclear axis, that means x and y axis, rotation is possible. So two rotational degrees of freedom, three translational degrees of freedom, and total degrees of freedom is 3, and means 3 into 2, 6. Here 5 has gone, so only one vibrational degrees of freedom. So formula is the vibrational degrees of freedom equal to 3n minus 5. So there will be only one vibration for a diatomic molecule, linear diatomic molecule. No bending vibration will be there, only stretching.
So that means oxygen molecule can come in this and hydrogen also can come this.
Yes, only stretching.
Okay.
Hydrogen, oxygen, carbon monoxide, HF, HCl. So only one stretching vibration degrees of freedom we will get. But if it is okay, that formula. If it is a non-linear, okay, triatomic, or let it be triatomic, number of carbon dioxide. Carbon dioxide is linear, so when it will be triatomic, the molecule may be linear, the molecule may be non-linear. Yes or no? So if
Yes.
it is linear triatomic molecule, then total degrees of freedom will be 3 into 3, that is 9.
Yes.
Okay, and vibration rotational degrees of freedom, that will be equal to 2, and translational degrees of freedom, that is 3. So same formula you can put 3 and minus 5. So 9 minus 5, that will be equal to 4. So vibrational degrees of freedom will be 4. How it will be 4? Let us consider the same one here. Some figure was there. Yes, here. See, it is the carbon dioxide. Linear molecule. So stressing, symmetrical, asymmetrical, and bending also. This type of bending vibration. So 4 vibration will be there. Okay. Theoretically, you can calculate and you can observe that one also. So where we are getting, you just see. If it is symmetrical stressing, it is IR inactive, because the compound which will be IR active, that should be polar. First, we have already I told the selection rule. The compound to be IR active should be polar. In this case, that the vibration is symmetrical, the compound is non-polar. But when it is asymmetrical, means both will be in this direction, some polarity will be developed due to induction of electron cloud. Induced dipole interaction. Okay, so due to that one, so it will infrared active, IR inactive. No, it's wrongly here. So asymmetric stretching, it absorbs at 2350 centimeter inverse, and this bending vibration, this requires lesser energy, so it will absorb in lesser wave number. Okay, so 4 types of vibration. It may be active or inactive. That is different thing, because if it is IR inactive, it should be Raman active. Both are opposite. The compound which is IR inactive, that will be Raman active. See, if a molecule has center of symmetry, then the vibrations are centrosymmetric and are inactive in infrared, but are active in Raman. Okay, we don't have Raman spectra, so just you have to remember which is infrared inactive, that will be Raman active. Any Raman active means it will absorb in the IR region, infrared region, but it will not give the IR spectra, it will give the Raman spectra. Okay, so and if it is non-linear, then the formula you have to remember, it will be 3n, here it is 3n minus 5, in that case it will be 3n minus 6 for non-linear molecule. As in case of water, what will happen? 3 translational and 3 rotational. So total 6 we have to subtract. So 3n minus 6. So like this, you have to find out how many vibrational degrees of freedom will be for benzene. Benzene contains 12 atoms, so total 36. 36 minus 6, so 30 number of fundamental vibrations will be there. Theoretically, there should be 30 fundamental vibration bands in infrared spectrum benzene. But it is not observed. Why? Because some will intermix with each other. Fundamental vibrations that fall outside the region under investigation, that is, it may be in the far infrared region or near infrared region. But we are considering only the infrared region. Okay, and some fundamental vibrations are also too weak to be observed as band, and they are so close that they can overlap. As in case of some figures we have seen, the band we are acting and they may overlap with each other. Okay, so this is the theory part. Then selection rule just discuss. And solvent effects are also there. Resonance effect, stretching and symmetric stretching, electromagnetic effect, that is electronic effect, that also give, and these are some fundamental vibrations of carbonyl groups. You can read here for formal same carbonyl group CO stretching at 1750, but when one methyl group is attached, the frequency decreases. Two methyl groups are there, as in case of acetone, the frequency of vibration still decreases. So that way we have to compare acetone, chloroacetone, what happens in chloroacetone? This is the minus I group is attached. Chlorine is having negative inductive effect.
Polarity will be created.
Hello?
Yes, sir. Polarity will be created.
Yeah. So minus I effect group is there. So the carbon bond polarity will be there. So it will be more stronger. That's why it will be observed at higher wavelength. Higher frequency. 1725. 1715 it increases to 1725. Two chlorines are there, 1740, like that way. So if due to electromagnetic effect, due to inductive effect, then it is increases due to increase in polarity. So all these factors you can go through that one. Then we'll discuss some specific examples. So we'll have a 5-minute break. Then we'll discuss the examples.
Okay, sir.
Okay.
Sir, your voice is not audible. Hello? Sir, I think you are muted.
No, I have not started.
Okay.
Okay, I'll start. Oh, sorry, I have shared the screen, that's why. Okay, this is fingerprint region. Then we'll move to the spectra. Okay, we'll discuss this one. What is the fingerprint region? They are divided into three regions again: 1500 to 1350, 1350 to 1000, then below 1000. So 1500 to 1350, that is mainly for the OH group and geminal dimethyl group. Other substituted benzenes, meta substitute there at here, monosubstituted benzene below 1000, and carbonyl, it occurs at 1300 to in between 1350 to 1000. The stretching also bending vibration. So if you consider this one, the appearance of doublet near 1380 and 1365, that represent the tertiary butyl group of the compound. Geminal dimethyl shows a medium band near 1380. Nitro compounds also, it will appear near 1350. Then 1350 to 1000, in that case you have alcohol, ester, lactone, acid anhydride. They show their characteristic absorption bands. Phenol also observed nearly 1200. Esters, they observe the carbonyl group is for the carbonyl group will show the peak at 1735. Besides that one, you will get a strong band between 1380 to 1050 for esters. And below 1000, will have the deformation of carbon-carbon double bond. So it will be around 970 to 960. So this region up to 1600, it is known as the functional group region. Functional group in the sense only carbonyl group, it will give around 1735 to 1750, and hydroxyl group and amine in 3500 to 3000, and methylene group around 2900. So these are functional groups, and fingerprint region tells about the stretching fundamental vibration of, let's OH stretching or CH stretching, like that way. But here we'll get the functional groups. Same thing, but as a whole, functional group can be detected from there. So let us move to the individual IR spectra, that is now alkanes and alkyl residue. So in alkane or alkyl residue, we have only the CH bond, either CH stretching or CH deformation. Nothing. Deformation means bending. Okay, let's go. So commonly two types of two CH stretching absorption, they appear just below 3000, that is around 2900. One for symmetrical and other for asymmetrical vibration, but they merge with each other, as in case of this one A and B. One is for symmetrical, one is for asymmetrical. Then the group of band correspond to CH deformation. the characteristics of alkyl group. Okay, so that is the deformation peak. Okay, the position of characteristic absolute equation 2962, that is for CH stretching. 2872, the B, that is for CH stretching in methyl group, the end methyl group, and this other CH stretching is 2962 methylene group, and 1460, that is for CH deformation, and 1450, that is for CH deformation again in CH2, one is in CH3, one is in CH2, and around that 772, that is the CH2, the rocking vibration. Okay, and this is like 3-methyl pentane. So in this case, it was just a straight chain dodecane. In 3-methyl pentane, as there is a methyl substitution, so the CH bending vibration in alkane that appear in the region 1485 to 1340, the vibrational absorption of CH bonds are much different from C bond due to the large mass difference. CH mass, reduced mass of CH bond and reduced mass of carbon-carbon bond is having little bit difference, mass difference, so there will be absorbance will be little bit differ. So the less characteristics and appear at weak band in the region 1300 to 800 centimeter inverse. So the spectra of isoalkanes differ from those of N-alkane in where 1500 to 700. So from 1500 to 700, there will be difference. You compare this one, whatever peak we are observing here, C, D, and E, here this is different. And this is 2,4-dimethyl pentane. You can see this part is enlarged. Here whatever is there, this is the just the zoom part of this one. Very weak peaks were there. So after zooming, we are getting it is clear. Same observation. Below, you see below 1500 we are getting all the stretching and bending peaks, and around 2900 we are getting the stretching peak of methylene and methyl group. So this table you can remember the CH stretching will be observed at around 2900 and CC stretching around 1300 to 800, and the deformation things you will get at 1485 to 1400 like the CH deformation in CH2, CH deformation in CH3, methyl group and methylene group. If a geminal dimethyl group will be there, then there will be another CH deformation. Sharp band, S indicates sharp, this is medium, this is wide. Okay, in case of alkene, you have a double bond. So for double bond, you can see the C will get the 1645 will get the carbon-carbon double bond stressing vibration. Other will remain almost same. 2960 again that CH stretching or methyl and methylene at a time we are giving, and 3049 for CH stretching in olefin for this one, around carbon-carbon double bond, whatever CH hydrogen is attached, that CH stretching is 3049. Other methyl and methylene, that you will get as usual, already we have discussed, around 2900. Am I clear? Any doubt?
No, sir.
Okay. Then moving to the cyclohexene. One carbon-carbon double bond will be there in cyclohexane, one double bond. And to that double bond, sorry, hydrogen is also attached. So double bond CH stretching, that will be observed around 3033 at higher frequency or higher wave number, whatever it may be. And rest is same around 2900, the CH stretching, around 1640 carbon-carbon double bond stretching. Okay, this whatever is there is just remember. You can remember all these things, or it will be difficult. Alkyne, again that triple bond CH stretching, again it move towards the higher wave number 3268, and rest remains same. And C triple bond C will get that one around this one, C 2110 new peak for C triple bond C stretching. C double bond C stretching will occur at 1600, and C triple bond C stretching at 2100. Others remain same, and one overtone will get for CS deformation at 1247. Cycloalkane, is cyclohexane. Cyclic one only noise is coming here, and rest peak will remain same as in case of alkane also. But for aromatic hydrocarbon, same aromatics A hydrogen stretching 3050 to 3000, carbon carbon double bond as I told in 1600. Okay, 1580 to 1600, carbon carbon double bond C double bond C for aromatic compound benzene, and deformation same 900 to 700 will get this one. So it is shown here for benzene around 1600. This is coming for C double bond C, and this is for the methyl group. Okay, ortho and rest part is okay. We move to other higher compounds. Okay, halogen compounds. Halogen compounds. The carbon halogen CCl, CBr, or carbon iodine, carbon fluorine, the stretching vibration, it will occur around C 800 to 600 or 500. So 800 to 600 for chlorine, 600 to 500 for bromine, around 500 it is iodine, and for fluorine, as fluorine is more electronegative, so we'll get at higher frequency, that is 1400 to 1000, you will get the fluorine. For chlorobenzene, you can see here, this is for CH, already we have discussed, and this B, C, all these things, they are for the carbon-carbon double bond, as you can see here, the position is given 3072 for CH stretching in case of aromatic, 1584, that is carbon double bond. The benzene ring, so the dotted bond is given because due to resonance. So it is around 1584 to 1478, and also up to 14. This B, C, and D. That is for benzene. So Cl stressing you will get as G and H. That is 735 and 702. Here, these two. G is not the G and H. G should be here. That is for CCl stressing. Similar for bromine, you can see the same thing. Bromopropane here, not benzene. Then for alcohol,
Sir,
alcohol will
pardon
get
here.
OH.
Hello.
Yes. Huh.
Sir,
Hello.
yes, sir. Here, uh, if we means this metal chelating, as you were telling, changes will be there. So during the changes, peaks will move upward or it will come downward,
Depends upon the
or
bond
no
strength.
such thing.
Yeah. No,
Acha,
no.
acha.
Depends upon the bond strength. How the polarization occurs. Generally,
Okay.
metals are more electropositive. So when ligand means it is giving the electron to metal, so polarity increases. So when polarity increases, generally it will absorb at higher wave number. Higher wave number. Would you follow?
Okay. Yes, sir. Higher wave number. This side.
Means if the amine absorbs at, for example, amine absorbs the NH2 stressing will be around 3000 to 3400. So when the amine group will make bond with the metal, okay,
Yes.
so polarity
Yes.
increases. So it will be still higher wavelength around, it will not up to 4000. So it may not be observed. It will come to the in near infrared region. Okay, that means
That
it will
means
come
it
below.
will shift like right to left this direction. I was
Right to
thinking,
left,
sir,
yes.
that top to bottom shifting.
No, that is observance only or percentage
Okay.
transmittance. But here the frequency
Okay.
will vary.
Okay, sir.
Transmittance has no role. Uh, Transmittance, whether it will increase or decrease, we don't have, we not, need not bother about that. And only we have to see the wave number or frequency, how it changes.
Okay.
Okay, so here
Okay.
alcohol and phenol. Yes, for alcohol and phenol, we have the OH stretching vibration, which will observe around this be above 3000. You see, the OH stretching for hydrogen bonded, so it will be around 3330, and rest is okay. Carbon hydrogen stretching 2900, same thing. And this one for primary alcohol will get another stretching vibration, CO stretching vibration. This is OH stretching, and this is CO stressing. That means alcohol means CO bond will be there, OH bond will be there. So for CO, we'll get the characteristics absorption at 1050. It is not up to the scale, not 1100, below 1100, it's showing above 1100. No, it is around 1050. Whatever written here, you just have to see, it is may not be exactly matched in this one. So for CO stressing, we'll get the peak here for primary alcohol. Similarly, if it is ethanol, you can see in carbon tetrachloride. So A, that this is for the OH group, A and B, and C and D for the methylene or methyl CH stretching for methyl or methylene group, and here 1100 around above 1000, whatever you are getting, that is for CO stretching. This is infrared spectrum for methanol. This is the OH group, is CH2 and again here CO stressing. Propan 2OL, that is isopropanol, and we get the same OH group CH2. This is CO stressing, and this is for the CH deformation and stressing vibration. So this is the table. You have to remember, not remember, to go through that one. Then we'll move to aldehydes and ketones. Carbonyl compounds. The carbonyl bond, as it is more polar, so it will absorb around 1700 centimeter inverse, and if unsaturated ketones will be there, they will observe at lower frequency as compared to its saturated analogs. So it's here that benzaldehyde. In aldehyde, there is no OH stressing or OH bond. So the broad band, the bonded OH region, and another very low. This is enolic. If keto-enol tautomerism will there, then there will be OH bonding. So that's why this is having some noise type, or it is a very broad band. So very broad band for bonded OH region, that is the this one, and rest of thing in here see the carbonyl group, which should occur at around 1700. So that is little bit less intense because due to the keto-enol tautomerism. Other examples we'll see this ethyl methyl ketone. So there is no tautomerization, you can say 15 around 1700 we are getting a sharp peak. You can see here 1715, that is CO C double bond O stretching. Rest is same CS stretching in methyl, so that is around 3000 and 2940. This they merge with each other A and B, giving a single peak. And the peak C is for CO stretching, and D, E, all are for CS deformation. Okay, all are for the CS deformation. Then okay, this is not required. Butyraldehyde, you can see the spectra of butanol or butyraldehyde. Then moving to at the esters and lactones. Esters means you have the CO double bond stretching and CO single bond also. So in that case, you'll get the CO stretching in ester, another peak will get around 1240. That is C single bond O stretching, and C double bond O stretching same at 1735, or in this case it is 1742. Moreover, the CS stretching, because this one the CH stretching of methylene group or what if the as more electronegative oxygen is attached to this methylene group, so it moves towards the higher frequency. 2900 is shifted to 3000, and rest part is okay. CS deformation and the CO stretching you will get here a new peak. Next, in case of carboxylic acids, as you know, in case of carboxylic acid, generally it dimerizes, so you will have a intermolecular hydrogen bonding. So therefore, and this is in carboxylate ion is in resonance form, so you'll get the peaks. As in case of heptanoic acid, the OH carboxylic acid OH band will be there, but it will be a broad band. The A started from here like this, and it mixed with the methylene group. This one 2950, and 3000 started from 3300 like this. It should be like, if it is sharp, it should come like this, then a sharp peak or CH stretching. Is written here, it is superimposed upon OH tracing. Both the bands for OH and CH both superimpose with each other, and characteristic spectra or carbonyl group, it is at 1715. So normal dimeric carboxylic acid and COH. So you'll also get around 1408. So in plain band you'll get like this. Noise will be there. Moreover, at 1280 and 930, you will get the CS stretching and OH deformation. Moving towards the acid halides, means when halogens are attached to the alpha carbon atom, the CO, C double bond O stretching vibration, that will move upward. If the electronegativity increases, then the absorption frequency it will increase. So if bromine will be there, it is 1730. If chlorine, then 1736 increases. Two chlorines increases to 1751. Fluorine in 1776 like this. So again, bromine, which is attached in a more remote place, then this is decreases. Electronegativity is same, bromine is attached, but it is remotely attached to the carboxyl group. So that's why it decreases. So this is for benzoyl chloride. You can see this A, which should be at 2900, shifted to 3080. That is for CS deformation. In case of aromatic ring and CO stressing, as chlorine is attached, it is at 1790. More electronegative, so attached absorption increased frequency or increased wave number. And 1745 you will get the Fermi resonance for the C double bond O stressing and a overtone of 875. Moving towards the anhydride. No difference, same type of spectra as in comparison to acids. You will observe here. Amides, for ammonia NH2 you'll get a same as in case of OH. We are getting the peak around 3400. Here for
Sir,
amides,
hello,
NH,
pardon,
yes.
sir. Sir, all amides will have same similar kind of this pattern, this spectra.
Yeah, all
Okay,
amides
means
depends upon.
depending on, yes, sir.
See, we are detecting the functional group here. So amide means, you see, you have a carbonyl group, you have an amine, okay. So because it will amide C double bond O, for example, it will
Hmm.
not influence very in a large amount to the amine group. If you have amine and amide, for example, okay, then what will the difference? Let this is amine, C double bond O,
Next.
this is not there, so it is CH2 NH2. So what peak will you observe? You will not observe this peak D. D is the peak for CO stressing, C double bond O stressing. So if it is amine, this peak will not be there. Rest is same.
Okay.
Now, if it is amide, you will get the peak for amine at A, that is a NH stressing, and another peak at D, which is the carbonyl group, C double bond O stressing. Would you follow? That is the difference.
Okay, sir.
Got the, got the point?
Yes, sir. Yes, sir.
So position will change, but yeah, you have to go through this one, and you have to just correlate. What here, do you break the functional groups? Amide means you will not get a single peak for amide. You will get a peak for amine, because we are getting the stressing. This is the stress, vibrational peak only. What type of different vibration will be there? So, and how this vibration is influenced? If it is simple amine, for example, then you will get the peak not at 3350. It will be less than 3350. It may be 3300 or 3200 something, the NH peak. Okay. But as it is a amide, that means a C double bond O group is attached to amine. So this group is more, oxygen is more electronegative. So CN bond is more polar. So due to that, the NH stressing, it will be in the higher frequency, which is 3350. Otherwise, it will be less than 3350 in case of amine. Got the point?
Yes, sir. Yes, sir.
Position will be little bit higher or lower, but it will be around the same one. Here is the for amine peak, here for carbonyl peak. If you mix, it will be amide. If this peak is absent, this is an amine. If this peak is absent, which one? NH2 or OH is absent, then it will simply a carbonyl group, not even in carboxylic acid. In carboxylic acid, you will get peak A as OH stretching. Here it is NH, whatever I have shown here, because it is amide. But if in carboxylic acid, COOH, so OH stretching you will get at A, around 3200 or 3300. Okay, it will be similar. Just we have to compare, because infrared spectra, whatever you should have should know the functional groups. You should expect what are the different functional groups should be there. Then only you can compare. And the exact functional groups you will know from NMR. If the proton NMR, you will get what are the number of protons are there, number of hydrogen atoms are in there, and whether it is attached to oxygen or whether it is attached to nitrogen, whatever may be. Okay, C13 NMR is there, proton NMR is there. So from there you can find out. So all these three, when you combine, or not three, four, mass, NMR, IR, and UV. UV is not much associated. NMR, IR, and mass. Then only you will find out the exact structure of the compound. If it is unknown, then you can predict. But a single spectroscopy, whether it is IR, NMR, only single. From that you should know what are the functional groups or what are the types of proton in case of NMR, what we'll discuss tomorrow. Okay, if you combine all these four, UV visible, IR, NMR, and mass, then only we can predict the structure of the compound. In the latter part, we'll discuss how to predict the structure. Some examples I'll give you and some problems also, then we'll solve them. Okay, it's lactam. What is lactam? It's written here. Okay, cyclic amides. Cyclic amides or amino acids are called lactams. That means they are cyclic. You have a C double bond O. To that one NH, nitrogen is attached. So what you will get here? The NH stretching also and the C double bond O stretching around 16 cc, 1700, 1690 it is coming. C NH stretching 3400 to 3500. Okay, if it is hydrogen bonded, then it is around 3300 to 3100 for hydrogen bonded. And for deformation, NH deformation 1620. Carbonyl stretching, if it is secondary amide 1700, now 1690 increases to 1700 to 1760. Then NH stretching, all these things will be there in the same region or little bit here and there. Benzamide. The amides, benzamide. Okay, amino acids as these are deuterions, so more polar. So that's why CO stretching occurs at 1754 to 1724, still higher. The asymmetric vibrational bond that for the double bond 1600 to 1560. As in deuterion, two vibrational modes of carboxylate ion are readily identified between 1600 to 1410. So amines already we have discussed. You see, there will be no carbonyl peak. C double bond O stretching is not there. See, one thing, because if you don't know the compound, then there will be confusion, because C double bond C, it is coming around 1620, and C double bond O stretching, it is coming around 17. In some cases, if less electronegative or plus I effect group will be there, then 1700 will reduce to 1680 or something. So they may come together. So in that case, there may be confusion, but you should know what are the functional groups, probable functional groups. You should know about that one. Okay. So like this we can predict. So that is all about the infrared spectroscopy. Next we'll discuss about NMR. Okay. Thank you. Or any doubt?
Sir, I forgot actually. I thought of. Sir, you were telling that enantiomers are having similar kind of pattern. So, if we are getting enantiomer, means how to differentiate that which one is present? Means what should be the next step that's to go for that
Go
we can
go for NMR.
NMR.
NMR, yeah. And optical rotation, optical rotatory, power you have to also observe, measure that one. Okay, other things are there, whether it is D or L, enantiomer you have to see. But if there is enantiomer, there will be noise thing. They will overlap, but we cannot detect whether it is D or L. For that, you have to go for optical rotatory power measurement. Okay, and more appropriate thing, it will give the NMR. From NMR, you will get that one. But here only we will get the idea that enantiomer may be present. Confirmation is NMR, more appropriate is the optical rotation.
And sir, what for then we should go for GCMS, just for molecular mass?
GCMS are this GCMS is gas chromatography and molecular mass
Mass
spectroscopy.
spectrum. Hmm.
Mass spectroscopy is coupled with gas chromatography. That means whatever sometimes when we carry out the gas chromatography, what is gas chromatography?
Okay.
What is gas chromatography? Liquid chromatography and gas chromatography.
Liquid
Here
to
the
LC.
mobile phase is liquid in liquid
Yes,
chromatography, and in gas chromatography, the mobile phase is a
that's
gas. So whatever gas is evolved, that is coupled. The chromatography is coupled with the mass spectrophotometer.
it.
So from
So
there we can find
actually,
out the mass.
molecular mass to find. So
Yeah, we
that
have to
will
find
be
out
a
the molecular.
supporting data to establish that what is the unknown molecule. That way, is it done?
Definitely. From there, we have to find out the molecular mass. Na? Parent peak will be
Okay.
there. Some daughter peak will be there. So, what will the fragmentation? How fragmentation occurs? So, basing upon the fragmentation, we have to find out what is the
So
probable structure
these
formula.
fragmentation, sir, these fragmentation will be doing by means individual analysis or for some means computer based or something is there, or if we have to read it by.
Everything. No. They are, for example, let us take here one molecule is there. Okay, this molecule you consider. CS3, CS2, NH, CS2, CS3. So what will the probable fraction? You will get a parent ion. Parent ion means only one, when one hydrogen will be removed. You will get one parent peak. The parent peak which is having the highest molecular mass in the mass spectrophotometer. That is the parent peak. Yes or no?
Yes, sir.
Then what are the different fragments? Different fragments, there may be an ethyl group, CH3, CH2, one fragment, and CH3, CH2, NH, another fragment, and there may be an NH fragment. Like these different fragments will be there, and different fragments peak you will observe. So that from that you can predict
Okay, sir.
that molecular mass of the compound is this much. Then you go for NMR. What are different types of protons are there? One methyl, three methyl protons, not three, six methyl protons, four methylene protons. This is symmetrical molecule, and one nitrogen proton. Nitrogen means proton attached to hydrogen attached to nitrogen. So one, two, three. Three types of hydrogens or protons are there. So like then what is the number or ratio of that proton? You have four one type, six another type, and one the third type. From the integration that we will discuss tomorrow. From that integration value, we have to find out the number of
Okay,
protons.
sir.
Then we can predict the structure. Okay, that is
Okay,
in
sir.
NMR.
Okay.
Okay,
Okay, sir. Thank you,
okay.
sir.
Thank you.
Okay.
Thank you.
Thank you, sir.